Okay, so we talked about this equation. We said let's come up with different cases for which the Prandtl number is Prandtl number takes different values, much less than one or much larger than one. As the case one, we picked the Prandtl number much less than one. We said it corresponds to this situation where the hydrodynamic boundary layer is much smaller than the thermal boundary layer thickness. And we said that at any moment where this equation is valid, when we are talking about this thermal boundary layer, most of the times you get exactly the same velocity value, which is v infinity almost for all the cases. That's the assumption we made. Now, let me say lecture 13. Boundary layer theory. Okay. Continued. Okay, good. So page 1. So let's write down this equation again, the equation that we want to solve. Okay. That was the Apple Pencil doesn't work. Oh my God. Oh, it does. Okay, the equation was d over dx. Let me make the thickness small is equal to, or maybe, let's go with this thicker version. Integral from 0 to delta t, vx 1 minus theta dy is equal to alpha del theta over del y at y is equal to 0. And we picked let's go with case 1. Nu over alpha is much smaller than 1. Okay. And we're going to do a similar analysis as we did in the momentum boundary layer theory. So let's write it down just like in the case of the momentum integral. We can assume a form of the temperature profile non-dimensional form, and polynomial, third order polynomial. Okay, so let us suppose theta, the temperature, is equal to A0 plus A1 y over delta t this time plus a2 second order y over delta t squared plus a3 y over delta t cubed. We wrote it in this way so that the a1, a0, so a0, a1, a2, a3 are unitless. Let's write down the boundary conditions to learn more about the coefficients a0, a1, a2, a3. What can they be? Boundary conditions. These are going to be similar to what we have done in the momentum equation. The first one is at y is equal to 0 at the fluid-solid interface. The temperature theta, the dimensionless temperature theta, is equal to 0. Because if you remember, it's T minus T vol divided by T infinity minus T vol. So your numerator is T vol minus T vol, which is 0. So the second boundary condition is at y is equal to delta t, theta is equal to 1, because that's equal to T infinity, T infinity minus T vol divided by T infinity minus T vol. And 3, at y is equal to delta t, the temperature profile saturates, meaning that it doesn't change anymore. Delta theta over del y is equal to 0. And also from the thermal energy equation, we have Vx del T over del X plus Vy del T over del Y is equal to alpha del squared T over del Y squared. And at y is equal to 0, we know that both Vx and Vy are equal to 0. One from the no-slip boundary condition, the other is from no penetration boundary condition. And this corresponds to the following: 0 equals, the left-hand side of this equation becomes 0, right? Alpha del squared T over del Y squared. From here, we get that at y is equal to 0, del squared T over del Y squared is equal to 0, or in other words, del squared theta over del Y squared is equal to 0. Okay, that's for our fourth boundary condition. Okay, and if you realize, these are exactly the same boundary conditions as those when we solved for the solution to the von Karman equation, right? So do we need to, I mean, why am I writing it here? Because the question is, do we need to redo it and to find these A0, A1, A2, A3? No, we don't need to redo it, because we know that those give us A0 is equal to 0, A2 is equal to 0, and A1 is 3 over 2, and A4 is negative 1/2. So I should just write down the solution, right? So we can say the solution must be thus theta is equal to 3 over 2 y over delta t minus 1/2 y over delta t cubed. That's our solution. Okay. So what are we going to do now? Now we're going to go back to this integral equation, right? This one. And we're going to substitute instead of Vx, we're going to substitute V infinity, because we know that for this case, so the Prandtl number much smaller than 1, we should get Vx is almost always equal to V infinity. So let's write it. Substituting Vx is equal to V infinity, since Prandtl number is much less than 1, and theta is equal to 3 over 2 y over delta t minus 1/2 y over delta t cubed into the non-dimensionalized energy integral equation. Gives you have d over dx, right? You have V infinity, you can take it out of the integral, 0 delta t, and then 1 minus your theta, right? 1 minus 3 over 2 y over delta t plus 1/2 y over delta t cubed dy is equal to, on the right hand side, we have alpha times, what was that? Del theta over del y at y is equal to 0. So basically, it's just going to be the constant term. So that's going to be 3 over 2 delta t, right? Because if you take the derivative of this part, you get some y terms, which gives you 0 at y is equal to 0. So that's the equation we get.
I have a question, Professor.
Sure. What is it?
So can you show one time again how did you went from the A0, A1 to 3 over 2 and number 2?
I couldn't understand, Domingos. Can you repeat
So
it?
could you repeat how we went from the constants A0, A1 to getting the format that we have 3 over 2 and 1 over 2?
Oh, so how did we get these 3 over 2 and 1 over 2? You're asking
Yes.
that? Oh, okay. So we say that we solved this equation before, but it was for V, right? Dimensionless velocity versus Y. But we had exactly the same boundary conditions. So we argued that we should get exactly the same solution. If you go back to, I guess, is that lecture 11? No, it was lecture 10, I guess. Let me go back here. You see, we found it. Let me check the lecture 9. It's not lecture 9. It must be lecture 10. maybe page 1. Yeah, there you go. See, Domingos, you have the same equation, exactly the same one, and you have exactly the same boundary conditions, right? Here the Vx over V infinity is 1, as our theta is 1, similar. So you should get exactly the same thing. Where is that? Where is that? Where is that? Yep. Yeah, if you use this, you see, we applied these boundary conditions. We found these A1 and A3 and A0 and A2 were 0. So I refer to this one. Okay.
Okay.
And let me know if you think there are any like differences between this and that, so that we need to redo it. So that's exactly the same analysis. So you should get exactly the same A1 and A3. Okay, so now we want to solve this. We want to do the integral on the left-hand side, but I think it's a good idea to simplify y over delta t, or change the variables. So let us change variables. So let's call y over delta t eta. Okay, and then from here you can get that dy must be equal to delta t times d eta. Right, so let's plug them in. You get d over dx e infinity integral 0 to eta is going to go from 0 to 1 because y goes from 0 to delta t, and thus when y is equal to delta t, eta becomes 1. 1 minus 3 over 2 eta plus 1/2 eta cube delta t d eta on the left hand side is equal to, on the right hand side, alpha 3 over 2 delta t. Right. And then you can take this delta t out, but you cannot take it out of the derivative because the delta t is gonna be a function of x. So what you get from here is basically, if you do this integral again, you should find 3 over 8 for the integral. Okay, v infinity can be taken out of the derivative. D delta t over dx is equal to alpha 3 over 2 delta t. Okay, and the 3's cancel. I mean, the part that I'm skipping here is that this integral without this delta t is already what we calculated before, and it's 3 over 8. Okay, and what do we get? So you can collect all the delta thetas on one side. So you get delta t's on one side. Delta t d delta t is equal to the constants 8 alpha, or you can actually simplify the 2 and 8, you get 4 here. You get 4 alpha divided by v infinity, and you have dx here. There you go. And if you take the integral, you find that the delta t squared over 2 is equal to 8, oh, sorry, no, not 8, it's 4 alpha over v infinity x plus constant, let's call constant c prime, but I can multiply both sides by 2 to get let me do it this way. Delta T squared is equal to 8 alpha over V infinity x plus another constant C. Let's call it C1. Okay. And what are the boundary conditions for the thermal boundary layer thickness? Do we know any boundary condition about it? At the leading edge, at x is equal to 0, the delta t must be equal to 0, because if you know from the profile it looks like this, right? This is x is equal to 0. The thickness here goes to 0 as x goes to 0. Okay. Okay. That's the boundary condition. So this gives you 0 is equal to 0 plus C1. From here, C1 is equal to 0. So what we found is delta T squared is equal to 8 alpha over V infinity x. But let's actually write down something dimensionless. Let's divide both sides by x squared to make the left-hand side delta T over x squared is equal to 8 alpha over V infinity times x, right? I mean, this would be 1 over Reynolds number if the alpha were equal to kinematic viscosity instead of thermal diffusivity. So you can do the trick that we did before. You can say 8 times alpha over nu. So you divide by nu and multiply by nu. Correct? And this term becomes exactly the 1 over Reynolds number. So get 8. And this term becomes the 1 over Prandtl number. Right? Is it? Yeah. So this is 1 over. Okay. Yeah, 1 over Prandtl number times 1 over Reynolds number. And then if you take the square root of both sides and then delta T over x becomes equal to 8 to the power 1/2. Reynolds number x, so this is Reynolds number x, by the way, negative 1/2. Prandtl number, negative 1/2. Okay. So this is valid for the case where the nu is nu over alpha is much less than 1, or Prandtl number much less than 1. Okay, but we haven't actually found the Nusselt number. We want to find out the Nusselt number because that's what bridges these analyses to the value of the heat transfer coefficient, right? So in an attempt to find out the Nusselt number, we write down at the boundary the following: negative K fluid, the conductivity of the fluid, del T over del Y at Y is equal to 0. This is a similar analysis as we did before to have an idea about the Nusselt number, right? We said that the conductivity right at the interface, but on the fluid side, on that infinitesimal small layer that touches the solid, equals to the entire heat flux from the solid to the fluid. T-vol minus T infinity from the Newton's law of cooling. So we said that that's the definition of the H. So whatever H is, H must satisfy this, we said, right? What you can do is basically you can divide both sides by T-vol minus T infinity, or maybe T infinity minus T-vol to get minus, Kf del theta over del y is equal to 0 is equal to H. So we divided by T infinity minus T-vol, which made the right-hand side negative, so it canceled with this negative. Okay. Do we know the value of del theta over del y at y is equal to 0? We had calculated it, right, before? I thought we calculated it. Oh, here. Calculated here. That's 3 over 2 delta t. So Kf times 3 over 2 delta t is equal to H. Already obtained above. When yeah, okay, so I can just write it that way, I guess. So from here, can we get the Nusselt number? Well, let's actually rearrange this to get H delta T over Kf is equal to 3 over 2. But Nusselt number x at the point x is x times h, hx divided by Kf. That's equal to H delta T over Kf. I want to make it look like this one, so I multiply by delta T and divide by delta T. So I get x over delta T, okay? And that's equal to, the first term is 3 over 2, as we found here, right? 3 over 2 times x over delta T. And we know what is x over delta T, right? We found it here. Delta T over x, it's 1 over this right-hand side. So you get 3 over 2, 1 over 8 to the power 1 second, Reynolds number x, -1/2, Prandtl number, -1/2. Correct? And from here, you get the Nusselt number x must be equal to, if you do the calculations, you get something like 0.53 Reynolds number x to the power 1/2, Prandtl number to the power 1/2. Does it agree with our earlier analysis? What do you think? Let's check. We had done some like order of magnitude analysis or something like a scaling analysis, right? Look at that. Isn't it wonderful? It's beautiful, right? We already had found earlier using scaling analysis that the Nusselt number scales with the square root of the Reynolds number, and the square root of the Prandtl number. For the case, Prandtl number is much, much less than 1. And it's basically the more accurate, although still approximate analysis gave us the same answer. Okay, and we just didn't notice the proportionality constant. Now we were able to calculate this proportionality constant. Okay, now let's look at another case, if you don't have any questions about this. So now let's say, let us now look at case 2. And our case 2 was Prandtl number, which is equal to nu over alpha, is much, much larger than 1. This means the following. Momentum boundary layer thickness is much, much larger than the thermal boundary layer thickness. So the picture is going to look like this. Your velocities look like this, but your temperature profile looks more like this. T wall, T infinity. So it saturates at a much shorter distance. So this much is delta T, and that's delta. Okay, so we cannot say that Vx is almost equal to V infinity this time, because in this region, as you can see, the velocity is changing a lot, right? Right, it changes from 0 to to some like finite values. Okay, what can we do? So instead, let us use the form of Vx over V infinity derived in the momentum integral method. I mean the following. So let's go back here. The assumption that the Vx is almost V infinity, we have used it here, correct? We have used it here. We wrote down V infinity instead of Vx, and now we say, oh, we don't need it. We can just plug in the value of the Vx here, because I know the roughly the estimate of the Vx from my previous analysis. So that's what I'm going to do. Okay. So Vx over V infinity from our earlier analysis, not from today's analysis, but from the momentum integral methods analysis, 3 over 2 y over delta minus 1/2 y over delta cubed, correct? And we had found also that theta was equal to 3 over 2. Even before like plugging in that Vx is equal to V infinity, we had already found that theta should be in the form of 3 over 2 y over delta t minus 1/2 y over delta t cubed, right? And it makes sense. You can say that when we had argued before that when delta, when this delta is almost equal to delta t, then this almost equals to this. So we actually argued that before, and it looks so. But now we're thinking about a situation where deltas don't compare. The delta is much, much larger than delta t. So this might have a different functionality than the other one, right? But I'm going to use the integral equation, right? So the the energy integral equation becomes d over dx integral from 0 to delta t Vx 1 minus theta dy is equal to alpha del theta over del y is equal to 0. So this becomes again, let's plug in y over delta t eta again. Okay. So let us say y over delta t, let this be eta, and thus y over delta, I'm going to have the y over deltas as well. What am I going to call them? So I should actually also figure that out. That's actually nothing but y over delta t times delta t over delta, which is basically eta times delta t over delta. Okay. So I can call this, let's call this n. How about that? Let's call this n. Yeah, let's call it n. Maybe we can actually, yeah, let's call it r, or maybe m. Yeah, let's call it m so that I do not confuse with eta. Okay, then we get y over delta is equal to m eta. Okay. We know that the m is much larger than 1, right? Is it? I'm sorry, let's see. So delta t is much smaller than delta. So that's much less than 1. I know, right? So let's see what happened to the integral equation. So I want to divide by v infinity and multiply by v infinity this thing. So I should get v infinity, d over dx integral from 0 to 1 vx over v infinity. We know from this that it's 3 over 2y over delta, which is m eta, minus 1/2 m eta's cube, and then 1 for the 1 minus theta, 1 minus 3 over 2 eta plus 1/2 eta to third power, and then dy is equal to delta t d eta. That's equal to 3 alpha over 2 delta t as we did before. So you just calculate this term at y is equal to 0 using this form, and you should get that. Okay. Let's do some simplifications. We know that m is much smaller than 1, right? So the third order power, we can actually approximately make it vanish. So you can get rid of practically it's 0. What you get is basically v infinity d over dx, and you have this delta t here. I take it here, delta t, and it's the only thing that changes with x. Integral 0 to 1, 3 over 2m eta. I just multiply everything with this term. this term. Yeah. Minus 9 over 4 m eta squared plus 3 over 4 m eta to 4, right? D eta. Oh, good. That's equal to 3 alpha over 2 delta t. And you get V infinity d delta t over dx 3 over 4 m eta squared minus 3 over 4 m eta to the power 3 plus 3 over 20 m eta to 5. And you calculate it between 1 and 0. It's equal to 3 alpha over 2 delta t, right? And you get V infinity d delta t over dx. And yeah. Okay, but I think I did something wrong here. Here is the thing. I guess that m is not a constant because m changes with delta t and delta. So since delta t and delta are functions of x, m is going to be function of x. So I should not forget actually that m is a function of x. So this derivative actually should act on m as well. Okay, so I should actually keep that in mind. Right? Okay, good. So I have this. I can take the m out and put it there, and then I calculate the rest. You should get something like 3 over 4 minus 3 over 4 plus 3 over 20. Right? That's equal to 3 alpha over 2 delta t, the right-hand side. Okay, so these cancel. You get, what do you get? V infinity 3 over 20 d delta t m over dx is equal to 3 alpha over 2 delta t, right? Now, let's write delta t as okay, here's what we can do. Let us write delta t as, from this equation, m times delta, right? And then the equation becomes, after simplifications of the 3's, and let's also simplify the 20 and the 2 and get 10 here. And you get V infinity over 10 d. Instead of delta, we write m delta. So we get m squared delta divided by dx is equal to alpha over m delta, right? Okay. So let's have a look at the delta for a moment. So the delta is changing with x. Yep. Okay, how can we make how can we simplify this further? Let's see. Okay. Okay, how can we make this more simplified? Let's see. That's right. Okay, let's take this m squared delta over dx is equal to 1 over m delta 10 alpha over v infinity. And then let's take the derivative of this left-hand side. We should get m squared d delta over dx plus the derivative of the m squared 2m d delta, 2m okay, the derivative of the first term. Yeah, so basically 2m dm over dx times delta. Yeah. So we are applying the product rule. We're taking the derivative of this plus this times this, and then the derivative of this times this. Okay. Is equal to 1 over m delta 10 alpha over v infinity, and then you multiply both sides by m delta. You get m cube delta d delta over dx plus 2 m squared delta squared dm over dx is equal to 10 alpha over v infinity, right? But we should at this point use some results from our earlier analysis, right? For example, what was the delta as a function of x? If I know it, I can just calculate the m as a function of x as well. So from our earlier analysis, we had said that delta over x for the hydrodynamic boundary layer, 4.64 Reynolds number x to the power -1 half, correct? So this is from momentum integral equation, our earlier results. So this also meant the following: del squared over x squared is equal to 4.64 squared nu over v infinity x, right? And the delta squared was 4.64 times squared times nu over v infinity times x, right? It was a linear function, the delta squared. And then from here, we knew that the derivative, the 2 delta, d delta over dx, I just want to find out this derivative, or hopefully maybe this thing, is equal to 4.64 squared nu over the infinity, and the derivative of x is 1, so just neglect it. And then if you substitute delta squared and delta d delta over dx into equation, let's call it star. Let's call this equation star. Okay. So we're going to plug in this one and we're going to plug in this one. We get m cubed 4.64 squared over 2 nu over v infinity, right? Okay, plus 2 times m squared times delta squared. Delta squared is this. Right? And then we have dm over dx. Is equal to 10 alpha over v infinity, the right hand side. There you go. So I can get rid of the v infinities. They're all in the denominator. I can get the news on the right hand side, right? So 4.64 squared okay, m cubed over 2 plus 2 times m squared x dm over x, so dm over dx, correct? Yeah, is equal to 10 alpha over mu. Alpha over mu is nothing but 1 over Prandtl number, so you can write instead 10 over Prandtl number. Okay, and then you get m cubed over 2 plus instead of m squared dm over dx, you take the derivative of the m cubed, so you get 2 over 3 x d m cubed over dx, right, is equal to 10 over 4.64 squared Prandtl number. So let's m cubed equals to z. Okay, let's call it z. And your equation becomes z over 2 plus 3x dz over dx is equal to 10 over 4.64 cubed Prandtl number. Now let's divide by 2x over 3. Get rid of this. And dz over dx is isolated. Plus you get 3 over 4x is equal to 3 over.
I think the sound is off.
The sound, okay, you cannot hear me? Okay, sorry. Can you hear me now?
Yes.
Okay. So we can have 4.64 squared Prandtl, and you have x in the denominator because we divided by 2x over 3. Okay. So you might have seen this from your differential equations, or maybe analytical methods course, or maybe calculus 3. This is equation is of the form dz over dx plus some constant pz is equal to q, a function of z, so a function of x. The solution to which can be obtained by multiplying both sides by the integrating factor. E to the power integral p dx. Okay. P not necessarily constant here, it's not constant either. So I just said it wrong, I guess. E2 integral, for our case, 3 over 4x dx, which is equal to E2 3 over 4 logarithm of x, which is equal to e to the power logarithm of x to the power 3 over 4. E to the power logarithm of x is nothing but x, so that's x to the power 3 over 4. So let's multiply with the integrating factor. Multiplying throughout by x3 to the 4th gives this equation x 3 over 4 dz over dx plus 3 over 4 x to the power 1/4 z is equal to 15 divided by 4.64 squared Prandtl number x to the power 1/4, right? And this is d over dx. You can simplify it as the x to the power 3 over 4 c. If you check, this is this quantity, and this is the derivative of this quantity, basically. Okay, is equal to 15. So this is basically inverse chain rule. So you go from here to here. 4.64 squared Prandtl x to the power 1/4. Okay. Now integrating gives, if you integrate both sides with respect to dx, you get x to the power 3 over 4 c is equal to 15 over 4.64 squared Prandtl number x to Prandtl number x to the power 3 over 4 over 3. Okay, and this is equal to 20 over 4.64 squared Prandtl number x to the power 3 over 4. Right? And then z comes out to be equal to 20 over 4.64 squared Prandtl number. Okay. And z was m cube. So m cube is equal to this quantity and the m was nothing but the delta T over delta, came out to be this, right? And now we can have an idea about the Nusselt number, finding a relation between delta T and delta. The Nusselt number x is equal to, as you know, h times x over kf. That's equal to h times delta T over kf x. I multiply it by delta T, and I'm going to divide by delta T x over delta T. Okay, and then this is h delta T over kf times x over delta times delta over delta T. Okay. And we had argued that this term is in the order of 1, right? I guess we had talked about this before. For this particular case, the h delta T over kf. And that's equal to x over delta times delta over delta T, which is basically from this solution. We have 4.64 to the power 2 over 3, Prandtl number to the power 1/3, divided by 20 to the power 1/3. Okay. And x over delta for the x over delta, what was the x over delta? Let's see. I guess my notes. Okay, so the x over the delta was, 1 over 4.64 Reynolds number x to the power -1/2, correct? Times 4.64 to 2 divided by 3, Prandtl number 1/3, divided by 21. Right? Okay. So from here we get 4.64 to the power -1/3 divided by 20 to the power 1/3. Reynolds number x to the power 1/2, Prandtl to the number 1/3. And this is basically equal to Nusselt number x is equal to 0.22 Reynolds number x 1/2. Oh, this is Prandtl number 1/3. Prandtl number 1/3. So that's the Nusselt number. And for this case, again, once you know the Nusselt number, you can calculate the heat transfer coefficient from the fluid properties and using this equation. Okay.